All right, everyone, I'm going to go ahead and begin the review. As usual, I'm recording and I'm going to post this review to YouTube later for the other students. So if you don't want your voice recorded, don't speak up, but feel free to type in the chat and I'll address your questions. And if you are comfortable having your voice heard by other people, feel free to speak up and chime in whenever you like. So first, some general comments about the test. It should be pretty familiar now. It's going to be the exact same as all the other tests in this course. That meaning it's going to be Thursday morning at 10:30. It's going to have the same amount of time as the previous tests. Yeah, it's really just the exact same. It's not a final. It's just test 4 in this course, and it just happens to be the last test of the class. So nothing different. Any questions on test policy? And again, feel free to chime in verbally or type in the chat. I will say, for those of you who don't remember, this is the test, if you, this is the test that can replace your lowest test grade. So if for instance, you got a 70% on test 3 and you get an 80% on test 4, well, that 70% from test 3 is going to get dropped, and basically your test 4 grade would count twice. So it would bring your grade up. I'll say this can only help you. It cannot hurt you. Okay. So if you do really poorly on test 4, it's not going to be weighted double. It's just going to be, okay, you have one bad test grade and then the other 3 grades are going to stay the same. Any questions about that? Okay. And as always, I'm paranoid that you guys can't hear me. Somebody type something in the chat to let me make sure you guys can hear me. Okay, excellent. You can hear me. So let's go ahead and review. We'll go ahead and start with content review. Again, I'm not going to go over in depth from each section. I'm just going to kind of give my expectations and maybe tell you guys what you can expect from the test. And then after the test, please feel free to ask me all the questions you want, okay? And I'll stay as long as you guys need. But starting with section 11.4. 11.4 is comparison test. So we're comparing two series. So maybe the most important thing you need to be able to do is deal with these inequalities, right? So real quick, let's say we have A, B, C, and D. Let's say these are all numbers and they're all positive numbers, okay? So you should be able to write inequalities like this. Like for example, if I didn't have an inequality sign here and I just had these two fractions and I was comparing them. Oh, somebody just asked, is the review homework mandatory or is it optional? Let's see, when is it due? I'm leaning towards optional, unless like 90% of the people have done it already because it's due tomorrow. Let's see when it's due real quick. I'll go ahead and say I think it's a good idea to do it, but let's see when it's due. Let's do the 29th. Yeah, so it's due tomorrow. It looks like. Let's see how many people have actually done it so far. If nobody's started it yet, then I'll just make it optional. Not many people have done it. Okay, so we can make it optional if you guys, yeah, maybe that's a good idea. give you guys more time to review. All right, so I'll go ahead and say, and I'll send out an announcement right now before I forget, review homework optional. What is it called? I can't do extra credit, just because, you know, I that's yeah, there's not a really good mechanism to do extra credit. So it's optional but recommended. Yeah, no problem. All right, so I would suggest, you know, checking that out. It is at this point, if for those of you who haven't done it, I would say go check it out. And, you know, now that the pressure of like getting it completed by tomorrow is, you know, taken off your shoulders, go in, look at it, and, you know, try it. You know, but, you know, obviously you don't have to worry about getting everything completed and 100% correct, but I would definitely look at it. All right, back to content. So for 11.4, we need to be able to look at a fraction like this and kind of think about this logically, like, oh, I'm adding, you know, this number up top is bigger on the right side, and the denominators are the same. So what does that tell me about my fraction on the right side? It should be bigger than my left side, right? So that's pretty straightforward. And if I subtract a number, okay, well then this should be smaller than this. So those may be straightforward, but and admits a lot of people get confused when this stuff is in the denominator. They see a plus sign and they say, okay, well, I'm adding something here, so that's got to be bigger, right? But no, you're dividing by a larger number. So your result will be smaller, right? So I need to have this inequality. Okay. And similarly, if I'm subtracting here, people see a minus sign and they think, okay, well, this number's got to be smaller, right? But it's in fact the opposite, because I'm dividing by a smaller number. And then we need to be able to put these together. So let's say I have this line here, and I want to write an inequality in the middle. Okay, I need to be able to think about this logically and say, hey, I'm adding a number up top. Okay, so this numerator is bigger than this numerator. And then I'm dividing by a smaller number over here, right? So this number on the left should definitely be bigger. Okay, so that's the kind of logic we need to be able to apply. Okay, so the most basic way we're going to see this is with P series, right? This is very common to see with P series, like or something close to a P series. So if I have n squared minus 1 over n to the power of 5, first of all, we need to find something to compare it to, right? So how do I do that? I kind of look at what's most important in my fraction. So that's probably going to be this stuff, right? All right, so I should compare it to this series n squared over n to the 5th, which just, I simplify that as 1 over n cubed, right? Okay. And then which way does my comparison go? Okay, I got n squared minus 1. And it helps to do the comparison before you simplify, right? I'm going to, you know, I could compare it to this or this, right? If I compare it to 1 over n cubed, maybe it's kind of unclear. But if I compare it to this n squared over n to the 5th, then my comparison should be pretty clear. I'm subtracting by a positive number on this left side, so that numerator is smaller. Denominators are the same. So I should have my inequality going this way, right? And then there's other conditions to check with comparison test, right? We need to verify everything's positive. Okay, so you know this isn't all the work. This is just an example of one way we would use it. We might also have something more complicated. Like maybe we don't have just a straight P series, or maybe we don't have just like n minus 1 over n cubed. Maybe we got something a bit more complicated. So you should hopefully be able to look at something like this, like ln of n over n, and compare it to something like 1 over n. So how do these compare? You should be able to have the logic where you can say, well, let's see, starting at 3, ln of n is going to be greater than 1, right? So ln of n over n should be greater than 1 over n for n greater than or equal to 3, right? So what does that tell me? Okay, this series, this 1 over n diverges. Since this is bigger, that diverges as well. Okay. So all I've just written out the straight comparison test. Remember, there's also the limit comparison test, which I'll abbreviate LCT. If you're going to use that on the test, don't abbreviate. Write out limit comparison test. If you're ever in any doubt about how much to write, I would err on the side of caution and just write more. More is usually better. People usually lose points because they didn't, they thought it was obvious and they didn't write it down. Okay, I've marked off on tests for you guys in the past because of that. So, just be safe and write everything. You can use limit comparison test as well. Remember, that's when we have series AN, series BN. Okay, maybe I know this converges or diverges. If the limit of AN over BN is equal to some number C, which is greater than 0, those series are going to do the same thing. Okay, so just remember that. And we can usually not always, we can usually use limit comparison test in all the same places we would use the normal comparison test. Okay. So I don't have a preference. I am not going to give you a question that says use the direct comparison test. Okay, maybe there's a question from 11.4 on the test. You can use either one. I mean, I'm not guaranteeing both of them will work, but if they both work, I don't have a preference on which one you use. I'll put it like that, if that makes sense. Okay. Any questions on 11.4 material? Okay. Moving on, 11.5 is the alternating series test. Fairly straightforward, I think. I'll just say one thing to remember is, okay, remember what that alternating series test says. Okay, we got this alternating sign term and then this numerical term, and we have this theorem that says, okay, if AN is what are the conditions? It's decreasing and the limit goes to 0, then it's convergent by the alternating series test. I don't think I'm missing anything there, but maybe I am. I think that's it. Remember, okay, what if the limit of AN does not equal 0? I've seen a lot of people, and this happens every semester, where, okay, the limit of AN doesn't equal 0, and they say, oh, it's divergent by alternating series test. No, we never say divergent by alternating series test. What test covers that case? Remember, that's from section 11.2 all the way back in the beginning of series. Okay, that's a divergence test. So you should never say something's divergent by alternating series test. Usually, if you're trying to say that, what you really want to say is divergent by divergence test. Okay, and that's really the only warning I have about section 11.5. Any questions on 11.5? And just remember that 11.5, okay, 11.5 is going to kind of pop back up in 11.6 and beyond, right? And this is really a warning about all the sections. For this test, even though the questions are coming from sections 11.4 through 11.9, or excuse me, 11.4 through 11.11, we really need to know like 11.2 through 11.11, right? Because maybe I'm not going to give you a question explicitly on like the integral test, but maybe for one of those power series, you have to use the integral test at some point, right? So we hopefully remember our material from those sections. And so this alternating series stuff, pretty simple, but make sure you got it down because it's going to be important for 11.6 and 11.7 and so on. So if no other questions on 11.5, I'll move on to 11.6. 11.6 was absolute convergence and conditional convergence. So remember, we have three methods to show absolute convergence, and this first one gets lost. A lot of people forget about this, just showing something by the definition. So remember, what do I mean by the definition? Okay, let's see an example real quick, a very important example. Let's say I have this series and I'm asked, okay, is it absolutely convergent, conditionally convergent, or divergent? Okay. Let's say you're one of the people who only do ratio test, root test, right? So you try ratio test, 99% of stuff is ratio test, right? You try ratio test on this. That would give you what? 1 over n plus 1 cubed divided by 1 over n cubed. Okay, and you take the limit of that stuff, and the limit of that stuff, what is the limit of this? This is just equal to 1, right? So think about what ratio test tells us. Remember, ratio test, root test, they both have these kind of three possibilities. The limit's less than 1, limit's greater than 1, limit's equal to 1. So we're kind of in this case, right? So ratio test doesn't tell us anything, and root test wouldn't really work on this. Maybe you could make it work, but it'd be pretty hard. So neither of those tests really work for this question. But this series is definitely absolutely convergent. And we can see that if we do it by definition. Okay, what do I mean by definition? We take our original series, right? This stuff in here is my an, right? What's the series absolute value of an? Okay, I just take all the absolute value of all that stuff. The alternating sign disappears, and I'm left with this series. Okay, that's my series of absolute values. And then I ask myself, okay, is this series convergent or divergent? Well, I know right away that's convergent by p-test, right? We have n to the power 3, 3 is greater than 1. It's convergent by p-test. So the series of absolute values, this converges. So by definition, my series is absolutely convergent. So don't neglect this kind of very basic idea, this definition of absolute convergence. Okay, that's very important. And then in other cases, we can use ratio tests, root tests. I think you guys are probably comfortable with those. Usually people get comfortable with these pretty quickly and kind of neglect this. But I would say revisit this idea of definition. And then before I talk about conditional convergence, are there any questions on these three methods? Okay. And remember, okay, conditional convergence. You know, this is something people have trouble showing a lot of times as well. How do we show something's, let's say I have a series AN, okay? How do I show it's conditionally convergent? Okay, so first of all, when do you try and show it's conditionally convergent? Usually what you'll do is you'll try a ratio test or root test and the limit's equal to 1. That's a clue that it might be conditionally convergent, right? We saw in this example that it's not guaranteed it's going to be conditionally convergent. We saw, okay, in this case, the limit's equal to 1, but it was absolutely convergent. But maybe, you know, maybe it's an indication that our series is going to be conditionally convergent if that limit's equal to 1. So what do we need to show? We need to show that this series of absolute values is divergent. And then we need to show the original series is convergent. And an example of this would be, you know, the most basic example would be this series here, that alternating harmonic series. Okay, so if I try a ratio test on this, I'll get limit equals to 1 from ratio test. Okay, so that's an indication maybe this thing's conditionally convergent. So I try it. I try showing my two things. I need to show these two things, right? So I consider my series of absolute values. When I do the absolute values, I just get 1 over n, right? And that's my harmonic series. I could just say divergent because it's harmonic series, or I could say by p-test because p equals 1. Okay, that's divergent. On the other hand, that the original thing, that alternating series, that's convergent by alternating series test, right? And again, I'm skipping a lot of steps in my conclusions, right? You guys need to show all the conditions for any test you use. But maybe straight away you can see it's convergent by p-test, or excuse me, convergent by alternating series test. So I've shown my two things. I've shown that my absolute values are divergent and my original is convergent. So by definition, that's, you know, conditionally convergent. All right. Any questions on 11.6 material? Okay. 11.7, remember 11.7 was kind of there was nothing new in it. It was just kind of a review section, right? That kind of gave you some general guidelines on how to solve lots of different series, or, you know, the kind of steps you should have in your mind, go through in your mind when you're trying to figure out if a series is convergent or divergent. So there's maybe one question that's kind of what I would call an 11.7 question, where I just give you a series and I ask you whether it's convergent or divergent. And you can use any method you want. You know, not all the methods are going to work, obviously, but I tried to pick questions that you could solve probably at least two ways, you know. So maybe you don't have to know every, you know, I don't think you have to be worried about knowing, like, well, you should try and know every test and all that material, but I'll say maybe if you're a little weak on one test or the other, you know, you should be able to solve this question in multiple ways. So, you know, for example, okay, maybe there's a question that can be solved by integral test or comparison test. So if you could do one of those two, all right, maybe you'd be good. But again, you know, I'm not guaranteeing which test it's going to be, so you should probably try and know them all. Any questions? 11.8. That's when we started getting into power series, right? So in this section, we introduced the idea of using ratio test and root test to finding interval and radius of convergence. And that's really all this section was about, right? Just finding interval and radius of convergence. So 99% of the time, it's going to be ratio test you know, maybe every now and then you'll see a root test. That gives you the starting point of your interval. You know, you do ratio tests, you find out the values of x that make sure that kind of guarantee your limit's less than 1. And then maybe that gives you an interval like from a minus r to a plus r. But remember, that doesn't tell you anything about the endpoints, right? We got to go in and test those endpoints individually by taking those values and plugging them into our series and seeing if it converges. And at that point, when we're plugging in these endpoints, again, all that material from 11.2 through 11.6 is up for grabs. Maybe I plug in this endpoint and I have to show it's convergent by integral test or by p-test or alternating series test and so on. So all that material is still up for grabs. Any questions on 11.8? Okay. 11.9, I'll go ahead and tell you guys right now, I haven't put any explicit questions from 11.9 on the test. That might change, so not a guarantee that it's not going to be on the test, but as of now, you know, I submitted my test to get approved, and it looks, you know, the comments they had, they didn't seem to mind that there was no 11.9 on there. So as of now, there's no question from 11.9. That could change, okay? So I'm not guaranteeing. But I don't, you know, the 11.9, the method in 11.9 is very specific. You know, 11.9 is all about comparing stuff to that one power series, this, and just playing with it to get a new power series, right? So it's so specific and so kind of niche that, you know, I prefer just knowing more general methods. You know, this stuff from section 11.9 you can usually do by 11.10, and you know, you don't have to memorize this 11.9 stuff. You can just do the 11.10 method. Okay. So 11.10, we need to know our formula, right? So we have formulas for Taylor and Maclaurin series. Okay, so if we're given a function, you know, I find my derivatives, I plug a into my derivatives, and then plug those numbers into my series, simplify, etc. I also still need to be able to find radius and interval of convergence, but it's not really too much new material except for this formula, right? Just that formula. So radius, interval of convergence, we know how to do those, okay, and we do them the same way we did in section 11.8. So not too much new there. But obviously it's kind of recent, so any questions on 11.10? Okay. And again, no, you know, I will use the terminology Maclaurin and Taylor series. So just know the difference. You know, it's not a big difference. A Maclaurin series is just when this a is equal to 0. All right. So it's not a huge technicality, but I will use this terminology on the test. So maybe I'll say find Maclaurin series. Okay, so you need to know that means, okay, that's my Taylor series when a is equal to 0. Last section. (11.11). 11.11 is kind of the section our entire chapter is building up to. It's these applications of Taylor series. And unfortunately, because it's just at the end of the semester, it kind of gets lost a little bit. You know, technically we're learning it, you know, right now, right? We kind of opened up the module on this section you know, yesterday. So I know it's short notice since test is Thursday, so we're not gonna hit it too hard, okay? But this Taylor series, Maclaurin series, and the Taylor polynomials are extremely important. I'll go ahead and say for all you like computer science people and engineers and stuff, these Taylor polynomials is really, these are really how your computers and stuff do math. You know, a lot of you might be saying, okay, why do we need to learn calculus? We can just plug it into a computer and all that, right? Well, how does your computer do it? It's this Taylor polynomial stuff. That's how when you plug 79 degrees into your computer or into your calculator, you do sine of 79. How do you think your calculator finds that? It plugs, you know, it has a Taylor series for sine programmed into it, you know, to, you know, maybe 100 terms of, you know, it's got this polynomial. What is the, let's see, it's x minus x cubed over 3 factorial, or something like this, right? So it's got this polynomial programmed into it. And then when you need to find sine of 79 degrees, it basically just plugs 79 into this polynomial, okay? This is this whole field of numerical mathematics, how computers do math, basically. And computer science people still have to program this stuff, and you know, this is ongoing. People have to rebuild this stuff all the time, so you got to have some idea of how to do the math to do that programming, I suppose. So it is still very relevant. That being said, my little spiel is now over. What kind of problems are we going to see? I'll kind of, you know, since again it's kind of short notice, I would say check out problems like example 2 in the book. I think that's a good one to look at. Example 2 in the textbook, where it's, you know, they give you sine of x equals, well, they say it's approximately x minus x cubed over 3 factorial plus x to the 5 over 5 factorial. You know, it gives you this Taylor polynomial approximation. And then it asks you, okay, well, if that's your approximation, what's the largest possible error in that approximation? And if you follow along with example 2, you should be able to find that. Just part A. Okay. I wouldn't worry about part B. So check out example 2, part A. I would, you know, also I would say example 1 is pretty good as well. I would favor this one. Example 1, parts A and B. That's a good one to check out. And then check, you know, section 1111 is not too long. I wouldn't worry about applications to physics very much. I will give you a quick application real quick if you guys are kind of wondering when you see this. And this is one, I think it's even more basic than what they give you in the textbook. Okay, I think most of you probably have physics 1. Physics with calc is required for most of you guys. Maybe you've taken it yet, maybe you haven't. Remember those formulas you got in physics 1? Like you were given formulas for the position of a particle, right? Let's say it's P of t. That's your function, your position of your particle at time t. Okay, and there were a lot of cases like constant velocity. Okay, well, what's your position? It was P of O plus your initial velocity times time, right? Well, VO, your initial velocity, remember velocity is just the derivative of position. Like if you have a position function, your velocity function is just its derivative. So really what this is okay. And then if you had constant acceleration, remember we had a different formula. Your P of t was what? P of O plus V of O times t plus A of O t squared over 2, right? But as we said, VO is just P prime. And then your initial acceleration, well, acceleration is just the derivative of velocity. In other words, it's the second derivative of acceleration. So what you have is this. And maybe this is starting to look familiar. You know, this is really the Maclaurin series. Okay, so the idea is, okay, this particle has some kind of true function that represents its position, but maybe we can only approximate it, or maybe we just know its derivatives. So we approximate the position of the particle by some polynomial. And that's where all those formulas come from. They're really just Maclaurin series. So again, a little off track, but I figured it was worth reiterating. So that wraps up my coverage of content. Does anybody have any questions so far? At this point, I'll open it up to you guys. I don't have anything else to tell you. But please feel free to ask questions if you have any questions about content or test policy, things like that. Now's the time. I'll stick around as long as you guys want, but I don't have anything else to tell you. Will there be any so somebody asked, will there be any instances of using the Taylor remainder theorem with Taylor approximations? I would say that Taylor remainder theorem is kind of critical for this example too, right? How do you find the maximum error? Well, if this is your approximation, the Taylor remainder theorem tells you, okay, the error, aka the remainder, is like what? It's going to be something like theta to the power 7 over 7 factorial for some theta. Maybe I'm approximating my function on the interval -1 to 1, something like that. Okay, so Taylor theorem is being used here. And then in this case, okay, well, we know, or let's see, this would be what? It would be like, it'd be like the 7th derivative or at some value of theta, right? Okay, so how, in this instance, what do we know? Well, we know, okay, it doesn't matter what point it is, right? The function sine, its derivatives it's either going to be the derivatives of sine, the 7th derivative of sine. It doesn't matter if it's sine or cosine, right? Sine and cosine are both less than or equal to 1. So I know that this term here is less than or equal to 1 over 7 factorial times what? X to the power 7, something like that. So that Taylor remainder theorem is being used in this problem, but I'm not going to give you something like, if I give you a problem on this material, it's going to be phrased like example 2. So I would definitely check out example 2, because if I give you a problem on it, that's pretty much exactly how I'm going to phrase it. Can we go over an example from 1111? Absolutely. So let me find an example I think you guys would benefit from. Okay, so let's just try an example from the, or problem from the book. Let's try just this first one. Okay. Yeah, you guys, as somebody asked, was that the baby just now? Yeah, my baby's in the background. Her grandmother's taking care of her at the moment. Okay, so this this question asks, okay, it tells you to approximate f by the Taylor polynomial centered at A. For degree n. And then part B is kind of what I told you guys to check out, that example I gave you. So this is part A. Part B says use Taylor's inequality to estimate accuracy of the approximation. Okay, so and Taylor's inequality is really just same as Taylor's remainder theorem. We'll say to find max error. Okay, so let's try part A first. So part A is kind of like a 1110 question, right? We want to find the Taylor, not Taylor series, but Taylor polynomial. Okay, so what would my Taylor polynomial be? I want a degree 2 polynomial. So let's see, I need a 0 degree term, a 1 degree term, a 2 degree term. Okay. So basically what I need is this. I'll kind of write it out symbolically first. Okay. So let's see, what's f0 of A? Remember, the 0 derivative, that's just the function itself. And I want it centered at A equals 1. Okay. So this first term, f0 of A, well, that's just 1 over 1. Actually, let's see, A equals, yeah. So that's 1. Okay. And then what's this term here? Well, the first derivative of 1 over x would be, let's see, negative 1 over x squared. And then I plug 1 into that. So I get negative 1 over 1, x minus 1 to the power 1. And then what's the second derivative? Second derivative would be, let's see, 2 over 1 cubed, which is 1. And this would be 1. So this is what my second degree Taylor polynomial looks like, which is usually kind of written as t sub 2 of x. Okay, so that's my Taylor polynomial. All right. Now so that's part A. Now part B, I want to find that maximum error. Okay, so what does Taylor remainder theorem tell me? It tells me that this remainder, this error, is going to be, let's see, it would actually be f of n plus 1, right? For some theta this should be, if we're doing a Maclaurin series, this would just be theta. But let's see, if we're doing a Taylor series, it'd be theta minus a, right? Okay. So my error should look like that. Okay. Now the problem is, okay, I know that the remainder is going to be equal to this, but I don't know what that theta is going to be. Okay. So first of all, let's figure out what this n+1 derivative is, right? Okay. So if I have a second degree Taylor polynomial, this stuff n+1 is going to be 2 + 1. It's going to be like the third derivative. It's all going to be in terms of that third derivative, etc. So what's the third derivative? Okay, so I have 1 over x. That's my zero derivative. First derivative, -1 over x squared. Second derivative, 2 over x cubed. Third derivative, 6 over x to the fourth, right? Okay, so this is my third derivative. And my Taylor remainder theorem tells me, okay, my error is going to be something like 6 over some theta power 4 divided by n+1 factorial. Well, n is 2 in this case, so 3 factorial. And then I got theta minus 1 to the power 3. So this is what my error term looks like. Okay. Now let's simplify a bit. I got 3 factorial here. That's going to cancel with that 6, right? Because 6 is just 3 factorial. So really what I have is this. Now, what's the biggest this can be? Remember, we're working on this interval 0.7 to 1.3. Okay. Okay, so what's the biggest this could be in that interval? Well, let's see. This is maybe a little bit confusing. An acceptable way I would think of this is that, okay, what's the biggest this could be and what's the biggest this could be? And kind of do those two pieces separately and then combine them. Well, what's the biggest 1 over theta to the power 4 could be? Okay, if I have this in the denominator, I need to make that as small as possible, right? Okay, so if I have 0.7 in that denominator to the power 4, that's going to be that's going to make this term as big as possible. On the other hand, how can I make, let's see, this as big as possible? Let's see, if I plug in 0.7 to this, it would be -0.3. So whether I plug in 0.7 or 1.3, I'm going to get 0.3 cubed, just with a sign difference. So this term here is less than or equal to 0.3 cubed. Remember, I'm taking absolute value, so if there's a negative sign in there, it doesn't matter. So that error is going to be less than or equal to, let's see, this should be to the power 3, right? No, power 4. Got it right the first time. So that error is going to be less than or equal to 1 over 0.7 to the power 4 times 0.3 to the power 3. So that should be the bound on my error. That would be an acceptable way to do it, obviously. This, I'll say, this is a bound for the error. There might be what we would call a tighter bound. So, you know, this method, you know, maybe my error's in here and I found these bounds. Maybe there's another method where you can get the bounds a bit tighter, but this method would work. And that would be acceptable on the test. Okay. One moment. Okay. Any other questions? Okay. I'm happy to, you know, keep doing problems if you guys want problems. But again, I didn't have anything in mind. So let me know what you guys want. If you guys don't need anything else, feel free to sign out. Again, I'm still recording, so at the very end, I'll post the video on YouTube, so you don't have to worry about missing stuff. But I'll hang around another 5 minutes, assuming there's no questions. If there are questions, obviously I'll stick around as long as need be. You're welcome. I'm glad you like the class. I'm teaching Calc 3 in the fall, if you guys, so you can either join my class or avoid my class. Yes, I'm the only, as far as I know, I think there's only one Excel section of Calc 3. So I would be the only Calc 3 professor for Excel. There, if you take it outside of Excel, there's obviously a lot of other professors. So if you're trying to avoid me, you know, that might make it hard for you. But yeah, I'm the only Excel professor for Calc 3 as far as I know. All right, well, I'll see you next semester then. Good luck on this test. Yeah, sure, I can do more problems from 11:10. Let's just do a new page. Okay, so let's try. So 16 from the textbook. We're given this function, and we're told, okay, find the Maclaurin series for this. And let's see, we also need to find radius interval of convergence. Okay. So again, for Taylor-Maclaurin series, we're always working off this formula, right? Okay. And for Maclaurin series, it's even easier because we just have this, right? Okay. So we're told to find the Maclaurin series for this thing. Okay. If you haven't guessed already, finding derivatives of this, that would be a pain in the butt, right? Because of all the product rule. You know, F0, okay, that's just x cosine of x. But once we get to the first derivative, okay, first derivative would be like cosine of x minus x sine of x. And then, you know, as we go further down, more and more derivatives, that would be complicated. You know, this term would keep splitting off, and on the second one, we'd have like 3 terms. On the fourth term, we'd have 4 terms and all that. Okay. But there's kind of 2 ways we could approach this. First of all, since this is a Maclaurin series, x is equal to 0, right? We're plugging 0 into these. So all these terms with x's out front would get canceled away because, you know, this x would be 0. So it'd be some trig function times 0. So it'd cancel out. And there's a lot of cancellations. And then we could also do, you know, maybe use a trick we learned in section 11.9, right? Instead of finding a Maclaurin series for this whole thing, maybe similar to how we did with like something like this, we found a Maclaurin series, or we found a series for this and then just multiplied it by x, right? We could do the same thing here. So instead of trying to find a Maclaurin series for this, I'm going to find the Maclaurin series for cosine of x first. Okay, so what would cosine of it? Well, let's call this g of x. What would this Maclaurin series be? Okay, so g0 would be cosine of 0. Let's see. Well, g1 be negative sine of 0, 0, g2. And then that pattern continues 0, 1, 0, negative 1, etc. So we end up with, you know, there's a table of Maclaurin series. We end up with that same Maclaurin series. If I'm doing it from scratch, maybe I can't see it at first, so I write out several terms. Okay, so let's see. The 0 term would be 1 over 0 factorial x to the power 0. First term, this term, say that'd be 0 over 1 factorial x to the power 1, so that gets canceled. Second term, that'd be negative 1 over 2 factorial x to the power 2, and so on. So I get this series that looks like this. Let's see how they wrote it. Should be able to write it like this. Okay, you guys can double check me on that series, but that should be our Maclaurin series for cosine. And remember, that's only part of it, right? We want to find the Maclaurin series for this thing. So I just multiply it by x. Okay. And if I'm multiplying that power series, that Taylor series, Maclaurin series by x, I can basically just ignore that summation sign. And if I'm multiplying these two things together, what happens? Well, this x combines with this x to the 2 to n, and I get x to the 2n plus 1. And then I'm going to stick my summation sign back out front. So that should be my Maclaurin series for that function, x cosine of x. So we saved ourselves a lot of trouble with product rule, right? We didn't have to do that, where we got all those terms and all that. It's a little trick there. I don't think, I wouldn't, I would say that's kind of complicated for the test. It kind of relies on knowing that trick. So I probably wouldn't give you anything, I'd give you a very basic Taylor series, Maclaurin series. Personally, I like the e to the negative, like the example that's like e to the negative 2x. I like the e functions a lot because they kind of work out nicely, a nice neat form, and they're not too crazy. So I would, if you're trying to practice, I would try and find a bunch of Taylor series, Maclaurin series for functions, the e functions, stuff like this. You can make up your own. Can we do an e function example? Yeah, absolutely. So let's just make one up. Okay, how about e to the negative 4x? Okay. The only problem I see, and I didn't do this on the test, but like, okay, I'm picking 4, so maybe the powers are going to get out of control. But let's see what happens when we do this. Okay, so let's say I'm trying to find a Maclaurin series for this. We can do a Maclaurin series and a Taylor series example for this. So let's say I have fxe is e to the negative 4x. Okay, and I want to find let's start with Maclaurin series. Okay, so again, I want to find all the derivatives, right? Okay, so the zero derivative, that's just the function itself. I'm doing Maclaurin series, so I plug in 0 for that. Okay, and I get 1. Okay, first derivative, negative 4 e to the negative 4x. I plug in x equals 0. I get, okay, negative 4. Second derivative would be 16 e to the negative 4x. I plug in 0 for x, and I get 16. And maybe you can see now what I mean by this is going to get out of control pretty quick. It's powers of 4, alternating powers of 4, right? So the third derivative, I can expect that to be negative 64. And then the fourth derivative, I expect that to be, that's what, positive 256, okay? So on. Okay, so now I need to plug these into my Taylor series. And this kind of works out nicely. Let's see, maybe now at this step, I could try and find my pattern here, okay? So what's my pattern with these? I know that's negative 1 to the power n, 4 to the n, right? Let's plug in a couple n's. So I plug in 0 to this. I'll get 1 times 4 to the 0, that's 1. Okay, I plug in 1. I get negative 1 times 4, so negative 4. Okay, so that checks. I plug in 2, I get positive 1 times 16. Okay, so it looks like it's working. So this is my pattern for my terms, my derivatives. I plug that into my series. And this is a Maclaurin series, so it's x to the n, starting at 0. So this one works out pretty simply, right? It's just I found my derivatives, found my pattern, and then just plug it in my series. And there's not even any cancellations to do at this step, right? There's no cancellations to do with factorials. So that's kind of why I like these. They kind of, you know, if you can find the derivatives and then find the basic pattern with the derivatives, you know, you can basically just plug it into the series and you're done. Okay. So this is the Maclaurin series for this. And again, we would need to find radius and interval of convergence, right? So let's go ahead and do that. Let's find interval of convergence. So we do ratio test. Okay. Okay, so I do an plus 1 over an, and I get something like this. And I simplify, I kind of get all the similar stuff together. Okay, I get something like this. I simplify. Okay, and then I take the limit of this. And what is the limit of this? Well, it doesn't matter what x is, right? This limit's always going to be equal 0. So this series is going to be convergent no matter what value of x I pick. So the interval of, what does that mean for interval of convergence? It's negative infinity to infinity. What's the radius of convergence? Infinity. You guys follow that one? Seemingly so. No comments so far. Let me know if you have any questions, obviously. We could have also done this as, so this was a Maclaurin series. We could have also done this as a Taylor series. The only difference is instead of plugging 0 into these derivatives, we would have plugged 1. Okay. So we could do this again. So let's say, let's do slightly different now. Let's do about positive 3x. And let's say we want to find the Taylor series centered at a equals, 1 would be a common example. If you pick something else, you're going to start getting weird values, right? These powers of 0 and 1 work out nicely. So let's pick a equals 1 and find the Taylor series for that function. So again, we start by finding derivatives. The 0 derivative, just the function itself. We plug in a equals 1, and I get, what, e to the power 3, right? Because I'm plugging 1 in for x. Okay. Do the first derivative. What's that? 3 e to the 3x. Again, I plug in 1, I get 3 e to the 3. Second derivative, okay, 9 e to the 3x. I plug in 1, I get 9 e to the 3. Okay, so it's nice pattern again. It's just powers of 3 times e to the 3. Okay, so let's try and write these terms. What are these terms going to be? Let's see, my first term, I can think of this one as being 1, going 1, 3, 9. Okay, so that's 3 to the power n, starting at n equals 0. And then I got this kind of constant here, e to the 3. So that's my pattern. It's 3 to the n times e to the power 3. So again, I just plug that into my formula. But instead of having x to the power n, I would have x minus 1 to the power n, right? And so it should be that. Now I need to do radius of convergence, interval of convergence again. Okay, so any questions so far on the series? Okay. Radius of convergence, interval of convergence. I do an plus 1 over an again. Okay, so ratio test. I'll do a quick ratio test. I'll skip some steps. Okay, there's no n's. There's no n's in this e to the 3, right? This e to the power 3, that's just a constant. Just like 4 or 7 or whatever. E to the 3 is just a number. So there's no n plus 1s in that. Okay. So that's my an plus 1. Then I divide by an, and I get, let's see, n factorial. Okay. Now I group all my stuff together. Simplify. These e to 3's just cancel completely, right? Okay. And again, okay, when I take the limit as n goes to infinity, it doesn't matter what x is, right? The limit's going to go to 0. So again, this will be another example where it's convergent. It's absolutely convergent everywhere. So interval of convergence would be this. Radius of convergence would be infinity. So I think, those would be two good examples of the E stuff. I'm not guaranteeing, again, even though this is a test review, I'm not guaranteeing that's what you're going to see on the test. So I wouldn't do anything super crazy. Like, for example, there's a problem in here that's like 1 minus x to the negative 2. It's not too bad, but I think this one would be a bit too much work finding, because you got a sign there that you're going to multiply by -1 every time, and it would get kind of ugly. So I would say like this would probably be too hard on the test. Something like e to the 2x. Okay, that's kind of in my opinion at the lower end of difficulty. So I think that's totally fair game for the test. You might see something maybe a bit more difficult, but a good starting point would be able to do something like this. Okay, any more requests or questions? I will say, if you're looking at the book, you do not need to know multiplication and division of power series. You don't need to know that from section 11:10. And I wouldn't say, you definitely don't need to know the binomial series either. You do not need to know the binomial series. If you're looking at the textbook, there's a table with all these Maclaurin series, Taylor series, and then table 1 in that section. You don't need to memorize that or anything. If you know this formula, you can recreate all. You can just figure it out. Okay, so if you know this, and you can do this process of finding the series, that's all you need to know from that section. Okay, and interval of convergence, radius of convergence. You don't need to memorize the whole table or anything like that. Just be able to do that method. Okay. Again, I'll give you guys a window. I'm happy to keep going. If you want me to go, give me some questions if you have questions. If not, I'll kind of give you a couple minutes of a window to figure stuff out. Then we'll sign off if nobody has anything. You're welcome.